Hello, grade 11s. Okay, so the next chapter or the next work we want to take a look at then is 2D and 3D wavefronts. We are going to be building on what you did in grade 10 again. What's very, very important to understand about this work is because we're going to be working with light, you're going to have to recall your work you did in grade 10 of transverse and longitudinal waves and all those things. But light on its own, we know that it's got a wave-like nature, and it's very difficult to show the path of light, like we can see in the diagram at the top there. It's very difficult to show the path of light because of this wave-like nature of it. So we make use of special tools in geometric optics to make it easier for us to describe how a wave front forms, what a wave front is, and how these waves actually act. So the first very important thing then is, what is a wave front? Now, a wave front can be defined as an imaginary line that connects waves that are in phase. Okay, so if we take a look at the diagram on the right hand side there, you'll see that we've got those three dots, which is our point sources, so that would be where the waves originate, and then they've got their concentric circles going out. Now, a wave front would be the orange lines. The wave front is the imaginary line that we perceive due to the motion of all these waves in the same direction. Okay, now points that are in phase can be anything. It can be peaks that are in phase, the highest point of a wave. It can be troughs that are in phase, the lowest point of a wave. It can be anything in between also. If we take a look then at some of the work you guys did last year, so we can say that wave fronts can show where constructive and destructive interference of a wave will occur. Now, if we take a look at constructive interference here on the right, we remember that when we have two waves that pass each other and they look exactly the same, they build each other up, so we get a higher peak and a lower trough. But destructive interference is when a peak and a trough overlaps with each other and they cancel each other out, either totally or to a certain extent, depending on the size of the two waves. Now, to describe wave fronts and the motion of waves, we make use of Huygens principle. Now, Huygens principle can be defined by saying every point of a wave front serves as a point source of spherical secondary waves after a time t. The new position of the wave front will be that of the surface tangent to the secondary wave. So let's say we work on this straight line. Okay? At time t, we have a bunch of point sources, and each one of them starts creating little secondary spherical waves. Now, the wave front that we see, because we don't see all these little tiny spherical wavelets, because all that is literally, let's say for instance in a water wave, the water molecules moving up and down, and we can't see that. Our eyes don't allow it. But what we see is that tangent to the outside of these circles, which is a straight wave front that is moving forward. Okay? And that allows us then to see how this wave just constantly moves forward. So, if we take a look at our initial wavefront with our initial point sources, and each one of them creates their secondary spherical waves, and we draw a surface tangent to those lines like in the yellow block there, that would be the new wavefront that we observe. Okay? And that then allows us to take a pattern or take a photo of this actual wave motion. So if we take a photo of the wave motion, we will see that we have different bands of light. Okay? The thick dark bands would be our areas of constructive interference. The white bands would be our areas of destructive interference, and in between is just the motion of the wave. And this allows us then to see how this wave actually moves. From there then, we need to describe certain characteristics of waves. So we have to take a look at something called diffraction. Now, diffraction is the ability of a wave to spread out in wave fronts as the wave passes through a small aperture or around a sharp edge. Okay? When this wave moves through a small hole, we don't have all the particles, original particles, moving in the original direction. So here on the right we've got Jack and Jill is calling Jack, so her sound waves moves in the direction of the doorway. But once it gets to the direction of the doorway, we've got only a few of the original particles making secondary spherical waves, and that's what bends this wave through that opening. Okay? It's the same as you sitting in your room while you're busy with your work. Your mom calls you from the kitchen. You know where the kitchen is, but it sounds like your mom's voice is coming from your bedroom door. And that's due to the fractions, due to this bending of the actual wave. So, if we take a look at the next example then, we will have that the original wave front is moving towards the small opening, but once it gets to the small opening, where we had a linear tangent in the beginning, we will now have, once it moves through the aperture, a bent tangent moving through the opening. So we find that diffraction taking place. Now this can happen in many ways. Okay, we can have waves moving through a narrow slit where we get a lot of diffraction occurring. We can have waves moving through a wider slit where we get less diffraction occurring. We can have waves moving through multiple slits where we have two different diffraction patterns overlapping. We get a degree of constructive interference and destructive interference. We can even have waves moving around an object, like we see with light a lot of times. Now, with these diffraction patterns, there's a couple of things we have to know. We have to know that each point on the wave front acts as a secondary wave or source of secondary waves. Each point source emits wave fronts from the edge of the slit. So there we have on the right, A and B are 2 point sources. The black lines on that diagram show the peaks in the wave emitted by the point source, and the gray lines represent the troughs. So those gray dotted lines represent the troughs. Constructive interference takes place where the solid diamonds are. So where we have a trough overlapping a trough or a peak overlapping a peak, we get constructive interference. Destructive interference occurs where we have those hollow diamonds, the clear diamonds, and that's where a peak and a trough overlaps. So we will find maximum diffraction or maximum constructive interference here in the middle band, where we get all of that massive buildup of constructive interference. So if we go and we take a picture above, or the picture to the right, sorry, it says above there, it should say to the right, sketches how the wavefront interferes to form a diffraction pattern. The peaks correspond to places where the waves are adding constructively, and the minima are the places where destructive interference take place. So we have here our laser, and our laser is sending out a wave pulse. Now as the wave pulse opens up, or as it hits that opening, we find that we get diffraction and the light bends through this opening. Now we've got two ways of indicating this diffraction pattern. We've got the above photo that we take, where we see there in the middle we've got a much wider central band, and that wider central band is our area of maximum interference, so our constructive interference. The light bands are our destructive interference, and the dark bands are constructive interference, and they constantly overlap with each other. Okay? Oh, sorry, one's wrong. The red bands, the thick red bands, like here in the middle, is the constructive interference. The dark bands correspond with our troughs, our destructive interference. And we always find our central band gives us an idea of the maximum diffraction that actually happened. We also have a set of rules for how we determine diffraction. So we can go and say that diffraction is proportional to the wavelength over the slit size. Okay? Where that little weird Greek symbol at the top, lambda, is our wavelength symbol, and the little W at the bottom is our slit size symbol. So we've got 4 rules. If we keep the wavelength constant, so let's say we make the wavelength 1, and we make the slit size very, very, very large, then we find very little diffraction. And from the formula we can see the slit size and the diffraction are indirectly proportional to each other. If we make the slit size very small, then we find that we get a larger amount of diffraction. We can do the same where we keep our slit size constant, but we change our wavelength because the two are directly proportional. So if we have a very large wavelength, we get a large amount of diffraction, and if we have a very small wavelength, we get little diffraction occurring. So just to show you again the two different ways that we can express this actually degree of diffraction. So I've got here the two slit sizes on the left hand side. So a wide slit size will give us our diffraction pattern. You can see there we have our diffraction pattern from the side, and there we have the photo that we take. So the central band here tells us the amount of diffraction that we're getting, and that peak there tells us the amount of diffraction that we're getting. If we make the slit size narrower, we get a much wider or much larger amount of diffraction. If we compare the two, we can see a narrow slit gives us more diffraction. If we then compare the effects of wavelength, now wavelength is very easy. The larger the wavelength, the more diffraction there is. And if we compare blue light and red light to each other, red light has a much larger wavelength, so therefore it has got more diffraction, as we can see from the two patterns here. We can take a look then at an example. We've got two types of light, green light and red light. Green light has a wavelength of 532 nanometers. Red light has got a wavelength of 670 nanometers. So already if we just compare the central band of the two, we can see that the red light has got a much larger central band, therefore more diffraction occurs in the red light. And we can do the calculations. If we originally said that the slit size is 1 meters, we can go and we can compare these, and we can calculate the diffraction of the green light and find it to be 532 times 10 to the power of negative 9. No units, it's just a comparison between wavelength to slit size. And the diffraction of the red light we find to be 670 times 10 to the power of negative 9. And what's very important there, we can immediately see numerically that we have a much larger diffraction in the red light. Okay, the only calculations that we can do in this chapter is just amount of diffraction. Okay, so I will do a separate video on motion of wavefront, just to take a closer look at Huygens principle, and then also just do another example of this wave or diffraction calculations.